Hi guys, welcome back. Before I continue, I just want to make some correction to the last video. There are two careless mistakes. Okay, I think one of them actually was over here. When I was using the quotient rule, I forgot to multiply the front by 2. Okay, so all of that, I kind of amended this LaTeX document such that the factor of 2 is multiplied to the front. Okay, ignore this first. I'll explain in a bit. Secondly, I think I did the integral equation sort of wrong. Yeah, wrongly. Okay, why was this wrong? Okay, so let me explain. Okay, let's see. I think there's a okay, hold on. Yeah, so this is the careless mistake here. Not only were the integrating factors wrong, I mean I forgot the factor of 2 in front. Let's see, this one was it should be a minus here. Okay, so that's the thing. Okay, if you check out Wolfram, you want to solve this ODE. This is y prime, and then you have y minus 0.75 over x equals square root x times a. If you were to look at Wolfram, you will see that this becomes the solution. Okay, I am a bit rusty, very rusty in fact, I think, with first order ODEs. So I'll just paste the solution here. Okay, all of this is wrong. Okay, all of this is wrong. Okay, so okay, I think the similarity solution part is also wrong, so just ignore. Okay, let's go up, and I'll go to the delta t cube part. Yes, see, all the way till here it is all wrong. Okay, so I'll begin verbatim so that I can paste this here. So this is what the solution is supposed to be according to Wolfram. Okay, the correct solution here is y equals to 4 over 3 a t to the power of 1.5 or x to the power of 1.5. Okay, plus arbitrary constant, plus the arbitrary constant x to the power of, what is this here, 0.75. so we'll just put 0.75 here. So this is Wolfram solution. Okay, Wolfram solution, I don't believe will go wrong. So if this is true, okay, this I'm just going to correct the mistakes here. So it's not going to be over 2.5 anymore. Okay, so it'll be 4/3. Okay, 4/3. But other than that, everything else kind of remains the same. Okay, other than that, everything else kind of remains the same. Delta t is going to be on the order of square root x. So I'm just going to put 4/3 instead of this 2.5 here. So let's do this. All right. So we'll do 4/3. And then the substitution will go on as per normal, but everywhere I see this 2.5, I need to replace it out by 4 over 3. So that's why everything is off. I mean, all these equations are pretty off. Okay, but the order of magnitude of x and everything is still the same. So next is still 4 over 3 here. I will not use x to the power 1.5 anymore. 4/3, 4/3, 4/3. All right. Now we should be ready to calculate the Prandtl number. So I'm just going to delete this part. ODE solving gone wrong. Okay. Okay. So never mind. We'll just use the Wolfram solution. Okay. I'm not emphasizing the math here. Okay. Use Wolfram wherever possible. It will save you a lot of pain, as I think you see very clearly. Okay, 4/3. Let's multiply this. I'll delete all of this. Let's just do 4/3. 4/3 times 15 times divide by 4.64 square. Okay, so this is the more correct number. So let's put this in 0.9289, 0.92895, 92895. Okay, 92895 it is. And then we will take the cube root of this number. Okay, which is about 0.9757. Okay, 0.9757. All right. You want to put a little bit more particular, you can put an extra decimal place there. So this should be the correct solution, but it still scales as Prandtl to the 1/3. Okay. So the similarity solution will be slightly different. It will be even closer to 1. So we'll just replace with 5 square. Okay, it will just still replace it with 5 square over here. Okay, so actually, yeah, why bother? You don't even need this anymore. That's wrong. Let's take that out. Okay, redundant and wrong. Redundant to use similarity solution and wrong number. Okay, so I'll just leave it here. I'll leave my mistakes for you to see so that you know what went right, what went wrong. Okay, so now now that we have this, we know Prandtl number scales, I mean the delta t over delta p scales as Prandtl number to the 1/3. Okay, so this all just ignore. Now the other thing is that from the Nusselt solution, there's this alternate method where you substitute the ratio of delta t over delta p. I've included all the steps over here just in case you want to take a look, so that you get the final ODE. Then of course you use Wolfram to solve this, but yeah, you just use Wolfram to solve this, so don't bother. Of course, phi will become your new y variable. Okay, so that one I'll leave it to you to. It's a goodies for you to go and take a look. Okay, so what's our heat flux? What's our heat flux? Okay, we have our dimensionless heat flux or dimensionless temperature gradient. At y equal to 0, and let's try getting the Nusselt number correlation. So that's 3/2 delta t. All right, that's 3/2 delta t. All right, 3/2 delta t. Now of course we can just quickly place in delta t equals to delta p. And that, yeah, delta t equals to delta p times all of this here. So delta p times all of this here. So let's bring out the Prandtl number. Oh shucks, yeah, let's bring out the Prandtl number. I think this is on the right track. Let's bring out the Prandtl number. Okay, times PR to the 1/3, and we replace delta P with the same thing. Delta P equals to, okay, fraction 4.64x over square root Reynolds number, the local Reynolds number. And there you go. I'm gonna paste this in. Okay, I'm gonna paste this in. Okay, I'll leave it there for you to see. Okay, so let's put it up. Let's bring this up so that on the upside there will be RE to the half. So there's Reynolds number to the half. Okay, so 4.64x will be at the bottom. Okay, so let's try putting some Nusselt number to it. Okay, so Nu equals to HL or Hx over K. So this is NUX, yeah? This is the okay, so what is H? Q equals to minus H T S, I can't remember which direction it was, so pardon me, minus T infinity. There's something along these lines. Okay. Okay, so if you're talking about conduction heat flux, okay, talking about conduction heat flux equals minus K partial K fraction partial T partial Y. Okay, you bring this yeah, I can't remember which side. Well, this is from wall to fluid. Okay, wall to fluid. Okay. So it's wall to fluid. It's just to make it clear. Oh wow, I need to underscore that. Okay, wall to fluid. So heat flux. So if the temperature at the let's see. Yeah, I keep forgetting. Okay, let's do this. Okay, so let's do a temperature profile. If let's say this is Ts, this is T infinity, and heat flux wall to fluid is equals to minus K partial T partial Y. So this is a downward sloping. Okay, so Ts minus T infinity. Okay, so this is not the correct signage. I have to swap around. So it's T infinity minus Ts. Yeah, this will be the correct sign. Okay, so just to make sure the sign convention is correct. Okay, sign convention has to be correct. Okay, so now we have this equation here. We are going to just swap it around until we can get theta. So let's yeah, let's swap it around. Actually, that's not much swapping to do. Just gotta make sure the sign convention is correct. Okay, so if heat flux from wall to fluid is positive, then this whole thing should be positive. There should be a negative temperature gradient. So if you forget your sign conventions, just draw the diagram out. I can't remember sign conventions for anything. So H equals to, or rather, fraction partial T partial Y equals to fraction H over K T infinity minus Ts. And remember our definition for theta. Okay, theta equals to T minus Ts, T infinity minus Ts. This is our theta definition. So in effect, del theta del Y equals to H over K. Alright, so just writing this all down again. Okay, it's because I just bring this T infinity minus Ts over, divide the left hand side, you'll get theta. Alright. Now we are in business. So this is the wall heat transfer coefficient. Okay. We are able to get our Nusselt number now. So we'll just bring the x over here. So I'll cancel this, and you have a hx over k. Then we have nux, yeah, nux. Nusselt number with x. Okay, so let's quickly evaluate 3 over 2. Because 3 divided by 2 divided by 4.64. Divided by 0.97573. Okay, 33.33 something. Okay, this is very close to similarity solution. 0.3313. Okay, perfect. Perfect. That's the answer we wanted. Very, very close to similarity solution. Oh, is it close enough? Not too bad. Not too bad. Okay, so NUL, you can do it yourself. I'm not going to do it for you. Okay, NUL is just twice of this. Okay, I'm not going to prove it here. You just have this times 2. 663. Okay, you have a 663. So just to make sure, I'll have it REX here. This one is REL. Okay, this one you prove yourself. Okay, I've done it so many times. Okay, so this is for Prandtl number, pretty big, yeah. But if you take a look at where we got that assumption from, let's say here. Take a look at where we got the assumption from. We were actually evaluating this equation here. Okay. Let's say your delta T and delta P are of the same order of magnitude, right? Delta T and delta P of the same order of magnitude. So 3 over 20 minus 3 over 280. So let's try that. 3 over 20 minus 3 over 280. Okay, it's not great, not that big at all. Okay, what am I saying here? Okay, because 3 over 20 How many percent difference is this? Okay, it's about 8% difference. It's not negligible, but it's not that big as well. So if you have a Prandtl number of 1, you can still afford to use all these equations here and this correlation over here as well. And even if your Prandtl number is 1, you can still afford to use this correlation. It's not that bad. You'll be about maybe 8% off in terms of boundary layer thickness. I mean, other than that, it's pretty okay. Yeah, of course, if you swap it the other way around, you will have let's see. Want to make sure that I get it right. If this delta t over delta p is much less than 1, okay, meaning to say the delta p is bigger. Okay. If I have a delta t, let's see. We have a delta p here. What does this show? Okay. You see this momentum? Momentum actually diffuses much more than the temperature. The momentum diffusivity is much more than the temperature. So what does it say? Nu over alpha is more than 1. Or Prandtl number greater or equal to 1. This is what delta p over delta t, or delta t over delta p more less than 1 implies. So this is the implication. Okay, so Prandtl number is greater or equal to 1. So not too bad. This is what you will get here. Okay, so what we are doing is for Prandtl number close to 1 or greater than 1. Okay, so these are all the equations relevant for that. For stuff that's not greater than 1, you will then have to do ODEs with the other side using this part. Okay, this is usually for Prandtl number much smaller than 1, usually for liquid metals. So this will have its own ODE on its own. I'm suggesting, well, yeah, instead of substituting your delta p in straight away, it is I think it's a lot better to substitute phi equals delta t over delta p. That means the ratio of these boundary layer thicknesses, and then you solve the ODE from there and use Wolfram so you won't get careless mistakes. That's what I would do. Alright, so that's all I have for you. Thanks for watching. See you again.